Okay, we'll get started then. All right, well, happy Friday. It's end of our first full week. So we'll continue. We've been talking about kind of Bayesian statistics, and we said in Bayesian stats we model things. We model unknown parameters as random variables, and so on Monday we looked at the beta distribution, and then on Wednesday we saw how we can take data that we've observed from a binomial or a sequence of Bernoullis, okay, and how we could use that to update our kind of our posterior distribution. So prior to looking at our data, we had a beta distribution to model kind of what we thought a player's batting average might be, and it would be a distribution, probability distribution, beta distribution, and then after we observe some hits and outs, we can update that. And we saw a few examples. You know, if you just have a few observations, it just updates it a little bit. If you have a whole bunch of observations, then it's going to have kind of a larger impact on how it updates, okay? Just a tiny bit of clarification. When we talk about the likelihood function of a binomial probability, it is not the same thing as the beta distribution, okay? So the likelihood function of a binomial probability, it looks a lot like kind of your beta binomial probability and whatnot, okay, or it is. So you have n choose z, theta to the z, 1 minus theta to the n minus z. And you can do this calculation using dbinom. This will give you kind of your binomial probability. And the d stands for density, and if it's a continuous function, it is the density. But then for discrete distributions, which is the case for the binomial, it would be a mass. So this is your probability mass function, okay? But the key here is that the z and n are fixed values based on the data that you've observed. And the unknown parameter is theta, okay? That is the variable, right? So the likelihood function of a binomial probability for n observations with z successes is proportional to, but not equal to, a beta distribution with shape parameters z plus 1 and n minus z plus 1, okay? And the key difference is that the likelihood function will not integrate to 1, whereas the beta distribution will. The beta distribution has that constant out in the front, so that when you integrate it, it integrates to 1, and the likelihood function does not integrate to 1. And I think I tried to clarify this, but on Wednesday's lecture, but I just kind of want to make sure that, you know, when we saw those likelihood functions plotted, they have been significantly amplified so that you can kind of see them on a similar scale to the other things. Okay, let's talk about inference. Now that we're kind of in this paradigm of Bayesian statistics and we're treating our unknown parameters as random variables, let's talk about how we would do some inference. Okay, so far we've been looking at the beta distribution along with kind of data coming from a binomial situation, and we call this the beta binomial model because the beta distribution is the conjugate prior to a binomial likelihood. So the observed data come from a binomial distribution. We say there are a total of n trials and z successes, and then when you do that calculation, the probability of success, you know, there's a constant here, but it is proportional to theta to the z, 1 times 1 minus theta raised to the n minus z. And then the prior distribution for the parameter theta, before we even look at the data, follows a beta distribution, and that's given by this. You have this beta constant, and then theta to the, you know, shape parameter alpha minus 1 times 1 minus theta to the beta minus 1. And so when you combine these together, when you multiply your prior and your likelihood, basically you're just adding the exponents, and you get theta to the z plus alpha minus 1, and 1 minus theta to the n minus z plus beta minus 1. And then in order for it to be a PDF where the whole thing integrates to 1, this becomes your new updated beta function coefficient here, okay? And so this thing will, this is, again, this looks scary, but it's just a constant so that the whole thing integrates to 1. Okay, well, we will go through and solve some of these things analytically. And we could say, all right, once you have this posterior distribution, what is the mean? What is the expected value? Okay, and again, the reality is we're modeling our unknown parameter as a random variable. So in reality, the unknown parameter could be one of infinitely many possible values. But you might want to know just, okay, what is the expected value of this unknown parameter? And so here we'll just say, hey, what is the expected value of this thing? And so if you have a beta distribution and your shape parameters are alpha and beta, okay, then the expected value is going to be alpha divided by alpha plus beta. So, and the proof kind of goes like this. So we're going to integrate across all possible values of theta, which in this case goes from 0 to 1. And then we're just basically doing the integral of, your random variable theta times the PDF of theta. And so when you do that, you can pull out 1 over b alpha beta right over here. That's just a constant, okay, with respect to theta. And this comes over here. And then so now that we have theta over here, this combines over here. And so this becomes theta to the alpha plus 1 minus 1, or just theta to the alpha right here. And because of the relationship that we had established earlier regarding what the integral of 0 to 1 is, okay, of this of something in this form, we can say this entire quantity right here can be calculated as beta function alpha plus 1 comma beta, okay, because basically we've just changed this exponent here. So, how does this work? Okay, well, the definition of this beta function is, gamma of, this term times gamma of this term divided by gamma of the two terms added together. So when you have 1 over beta here, beta function over here, you get this gamma function. And then over here, you have gamma of alpha plus 1, gamma times beta, and then this is gamma of alpha plus beta plus 1, okay? And one way to think about the gamma function is a lot like the factorial function, but just made continuous, right? So if you think about, gamma x plus 1 is the same thing as x factorial. So gamma of 5 is the same thing as 4 factorial. And it's just kind of like, when you have 3 factorial, 3 times 2 times 1, which is 6. And if you have 4 factorial, it's 4 times 3 times 2 times 1 is 24, and then 5 factorial is 120. And what if you had a kind of a smooth continuous line connecting all of those dots? What would that look like? Okay, that would be your gamma function. On the negative side, it gets really wonky, because if you think about what is like negative 3 factorial, then you have an odd number of negative numbers. And then if you have negative 4 factorial, then you have an even number of negative numbers. So it switches from negative to positive. And the gamma function also kind of takes that into account. So the negative side of the gamma function is really crazy looking, okay? But the right-hand side of the gamma function, the positive side, is just, again, kind of like the factorial function, but if you just connected it with a smooth line, okay? And so the definition one definition of the gamma function for at least integers, okay, is if you have an integer gamma of x plus 1, it's equal to x factorial. So if you think about what that is, that can you can kind of take a recursive definition of the factorial function, and you can say, well, gamma x plus 1 is going to just then be x times gamma of x, right? Because gamma of x would then just be the factorial of x minus 1, and so on and so forth. So we can kind of take this recursive definition of what the gamma function is, and so extending all of that out, okay, here I've got gamma of alpha plus beta, and then gamma alpha plus 1 becomes alpha gamma alpha, and then gamma beta here, and then we've got gamma alpha gamma beta, and then over here I've got gamma alpha plus beta plus 1, which becomes alpha plus beta times gamma alpha. Okay, well anyway, all of this, and you can kind of eliminate all the things that are in common in the top and the bottom, and you're just left with alpha divided by alpha plus beta. So all to say is if your shape parameters are 5 and 5, your expected value is going to be 5 divided by 10. And your expected value would be 0.5. If your shape parameters are 1 and 99, then your expected value would be 1 divided by 100. And your expected value would be 1%, and so on and so forth. And that would just be kind of your average there. So that's the mean. The mode is basically where the peak is. Where's your peak? And that's going to be found at this location, alpha minus 1 divided by alpha plus beta minus 2. And so the way we calculate the mode for the beta distribution is we're going to take the derivative of the beta distribution with respect to theta. We're going to find where that derivative is equal to 0, so because we're looking for the maximum, and then we solve for that. So here I'm going to take the derivative of the beta function here, and so this is just kind of the multiplication rule. So this is a constant we pulled out ahead. This becomes alpha minus 1 theta to the alpha minus 2 times, what is the derivative multiple? U times v is like what, u dv and v du, or something like that when you do derivatives of that. So anyway, that's what we got going on here, okay? And so you can kind of follow all of the math. Alpha minus 1 theta to the alpha minus 2 times 1 minus theta to the beta minus 1. And then, v du will have theta alpha minus 1, and then this becomes beta minus 1, 1 minus theta to the beta minus 2, and then we have a chain rule on the negative theta, so we have negative 1 there, okay? And then we're going to set this whole thing equal to 0, and we want to solve where everything is equal to 0, okay? Now, kind of the trivial cases, all right, so when we set this equal to 0, the trivial cases that the derivative is equal to 0 when theta is equal to 0 and when theta is equal to 1. Okay, so because if you think about what all of your beta functions, they basically 0 and 1, and you've got basically a derivative of 0 over here and a derivative of 0 over there, and then we're really also looking for where the derivative is right here. This is going to be our one. So these are the trivial cases, so we'll just kind of factor out or just get rid of the theta to the alpha minus 2 and the 1 minus theta to the beta minus 2. And we're just really going to solve for where this part is equal to 0. Okay, so I've got alpha minus 1, 1 minus theta times theta beta minus 1. Okay, so multiplying all of this together, first, outer, inner, last, we get alpha minus 1 minus alpha times theta plus theta minus theta times beta plus theta, and so you can gather all of your terms together, and so all of these ones have a theta in common, and these ones do not, so we'll have alpha minus 1 minus theta times this quantity, and again we're solving for theta, so I'll bring this over here, and then we can say theta is equal to alpha minus 1 divided by alpha plus beta minus 2. So this would be kind of where the mode is, where the derivative with respect to theta is equal to 0. So that would be kind of where our peak is. And so we can see, if so the mode tends to just be a little bit just slightly different from where the mean would be, okay? So if your mean is located at alpha divided by alpha plus beta, so if alpha and beta are equal to each other, then your mean and the mode are at the same location. So so if you have alpha is 5 and beta is 5, Okay, your mean is at 0.5, and then over here you would have 4 over 8. Your mode would also be at 0.5, okay? But the mode tends to kind of get pushed a little bit more towards the edges. So for example, let's say alpha is 2 and beta is 8, okay? If alpha is 2 and beta is 8, your mean is going to be at 2 divided by 10.2, whereas your mode will be at 1 divided by 8, will be at 0.125, okay? So the modes get pushed a little bit. And that kind of makes sense, because if you think about distributions like this, okay? Your mode is over here, but this is right skewed, okay? So if here's your mode, your mean is going to get pulled a little bit in the direction of the skew. That's your mean. So your mean gets pulled a little bit closer, and your mode is closer to one of the edges. So that's basically all this is just reflecting that. All right, let me give you your first view quiz answer, which is the letter A. A as in apple is your first view quiz answer. Right? Yes. Okay, A. All right. Okay, so with Bayesian statistics, instead of confidence intervals, we make actual probability intervals, okay? And so, in frequentist stats, when you learned about a confidence interval, we said you can only say I'm like 95% confident, but you weren't allowed to use there's a 95% probability. With Bayesian stats, because the unknown thing is a random variable, you can now use the word probability, and that's fine. So yeah, in frequentist statistics, the unknown parameter is fixed, so we can't talk about the probability that the parameter falls within some chosen bounds. We always use the word, I'm confident that it falls within these bounds. But in Bayesian stats, the unknown parameter is a random variable, so it is subject to kind of random forces. And we say there's a 95% probability that the parameter falls within the chosen bounds. And so we have a couple kind of methods we could use for determining the bounds of the interval. And so one is we have the equal tail credibility interval, and the other is the highest posterior density interval. These are just long, I guess they're descriptive. All to say is this is what it looks like. Okay, so to kind of illustrate these, I'm switching over to a completely different distribution, and this is the gamma distribution. So I don't feel like getting into what exactly the gamma distribution looks like, but this is just so that like my numbers look a little bit more different, because if it was the beta distribution, yes, there will be differences, but it'll be like so small because everything's on 0 to 1. It's a little bit harder to notice. So with the gamma distribution, it's a little bit easier because now you're dealing with numbers that are bigger than 1. Okay, but just know that we're kind of switching things up here. So with a gamma distribution, you might have, let's say your posterior distribution is this gamma distribution. It looks something like this, okay? And again, in this case, the lower end is at 0, and then the upper, technically, it goes, pretty far. I want to say up to infinity here, but much more than 10. It's really small. But anyway, the idea here is the equal tail is you're looking for 95% in the middle. So you're going to have 2.5% here and 2.5% over here. Okay, and you'll notice, so this is 2.5% and this is 2.5%. You get 95% in the middle, and you can do this by using the Q function. So every density function you have D, and you have P, you have Q, and you have R. So D is basically your probability function. This is your density. Basically your PDF or your PMF, okay? P is going to be your cumulative distribution function. That's going to be your CDF. And then Q is basically the inverse CDF. Okay, and then R is for random generation. So here we want to find the inverse CDF. We want to find, okay, the location that's going to give me 0.025, the 2.5th percentile and the 97.5th percentile. And it says, okay, those bounds are going to be 1.08 and 6.82. That's right here and right here. That's your equal tail credibility interval. The other is your highest density interval, okay? The HDI, and so there is a library that calculates this for you, because otherwise it's a little bit of a pain. And so the HDI, it's kind of like you still have the goal of you want 95%, okay? But now we're kind of like dipping the density PDF into like water, so that the height of the lower and the right hand side are the same heights. Okay, so you'll notice we get different values here. Okay, the lower bound is 0.8 and the upper bound is 6.28. Okay, contrast that to over here. Our lower bound was 1.08 and over here, our upper bound was 6.82. Here my lower bound is 0.8 and my upper bound is 6.28. Okay, and it looks like this. And the idea here is that the height of the left-hand side and the right-hand side are the same height. Okay, this is the highest density. Okay, and so you'll see that the left-hand side area is only 0.008 and the right-hand side area is 0.042. So the center area is still 95%. It's just your right tail and your left tail are different sizes. The highest density interval has the property of having kind of the smallest width. So if you take the difference between 0.8 and 6.28, that will have the narrowest width of what your probability interval is going to be. So the width of this one is a little bit wider, and this is going to be the narrowest width that you can have. Okay, but both of these are both 95% probability intervals. Okay, you have a 95% probability of falling in this center area, and you have a 95% probability of falling in this center area. Okay, is one better than the other? I don't know. That's just the creation of the intervals there. Okay, so whether you select the equal-tailed interval or the highest posterior density interval, it is correct to say that there's a 95% probability that the unknown parameter falls within the bounds of the interval. Okay, and again, this reflects kind of our subjective belief about the random variable. And when we say subjective belief, basically we're saying we're combining our prior knowledge, how we decided to model the data before we even saw, or how we decided to model the unknown parameter before we even saw the data. Okay, so if we're talking about the baseball example, I said this is going to be the shape of the distribution before we even looked at the data. Okay, and then we combined that with the data we saw, and so that still reflects kind of our subjective belief. And nobody likes this term subjective, but it is true that somebody else could have used a different prior distribution, right? So I used a prior distribution with shape parameters 81 and 219. Somebody else could have used, a prior distribution with shape parameters, 75 and 225, or 70 and 230, or something. Other values, and they wouldn't have been wrong. Okay, I mean, again, wrong is a little bit. There isn't a right or wrong. It's a little bit subjective, and you kind of try to back up you justify your positions and whatnot. And so, when you're first starting out with Bayesian statistics, this part's probably the part that's most uncomfortable, the idea that things are subjective. But I think if you start thinking about statistics, there are so many things that are a little bit subjective, in that, like, all of these other models that we quote they're based on so many assumptions, okay? And all of these assumptions have to be true in order for the model to even work in the first place. And someone might ask, why are you making that assumption, and so on and so forth. So anyway, the truth is statistics is trying to make sense out of real life data, and guess what? Real life data is messy and complicated, and you do have to make some assumptions and take some subjective stances in order to kind of even move forward, okay? So I know a lot of people are uncomfortable with the idea of subjective, but to that I just say, you'll get over it, okay? All right, so the credibility interval incorporates our prior knowledge in the form of the prior distribution used in the calculation of the posterior distribution. We just multiplied our prior with our likelihood. And what we saw, and this is just the case for all of Bayesian stats, is that in cases where you have little observed data, okay, your credibility interval, or basically your posterior distribution, is greatly influenced by your prior beliefs. So if you only have a little bit of data, you're going to rely more heavily on kind of your prior beliefs and your, what you're expecting in the beginning, okay? As you get more and more data, in cases where lots of data is available, then the interval is more influenced by the data, okay? And that's true not just in Bayesian stats, but like all of life, right? When you first kind of experience something, okay, most of your kind of thoughts and beliefs about it are coming from prior, and then as you get more and more familiar with it, then the actual data in your experience starts to color things in a little bit more, okay? Meanwhile, a frequentist confidence interval, on the other hand, is determined only by the observed data. And so in a frequentist situation, if you have little data, you end up with these giant margins of error. And then as you get more and more data, you get smaller margins of error. And so frequentists, obviously rely on having lots of data. And Bayesian stats kind of relies on having some prior beliefs, okay? We talked about conjugate priors. If the posterior distribution and the probability are in the same probability distribution family as the prior probability distribution, then we say these are conjugate distributions, and the prior is called a conjugate prior. The beta and binomial are a pair of conjugate distributions, and then we have kind of this table of conjugate distributions, which I think I showed you guys on Wednesday also. All right, so how do we go about making predictions, okay? So we want to, let's say we've gone through this process, we have the posterior distribution, and how do we use that, okay, to kind of make predictions and whatnot? So we'll revisit our baseball example. We said prior to looking at our data, okay, the prior distribution for theta is a beta distribution with shape parameters 81 and 219. Oops, 0 over here, 1 over here, and kind of the shape was something like this, where kind of the mean. So this is our prior, where we had shape parameters 81 and 219, and then we had observed a new player who started off their season with good performance, had 10 at-bats and 5 hits. And so based on that, okay, we adjusted, and so our posterior distribution is now just ever so slightly shifted to the right, okay? So this one over here is the prior, and then this one over here is the posterior. Okay, and so after observing high performance, we've adjusted our posterior distribution to just kind of shift over to the right a tiny bit. Okay, and so if this is our posterior distribution, we can ask this question: if this player has 3 more at-bats at the next game, what's the probability that he's going to get exactly 2 hits? Okay, what's the probability he gets 2 hits out of the next 3 at-bats? Okay, so the question by itself is basically a binomial thing, right? Binomial, you have n equal to 3, and we want to know x equal to 2. But right now, the question is, what do we use for theta? Okay, your answer for binomial would be 3 choose 2, theta to the 2, 1 minus theta to the 1, okay? But your answer really depends on what theta you're going to use here, okay? And the issue is that we don't have a single value for theta, okay? Theta could technically be any value between 0 and 1. We have a probability distribution that says some values of theta are a lot more likely, and other values are not as likely, okay? So here's a few options, okay? One is you could just say, all right, let's use the mean, plug that in, okay? Just use a single value, let's plug in the mean of the posterior distribution and get a number, okay? Another is, let's use the mode of the posterior distribution. Let's use a single value and plug that in, all right? And then another is, what if we do an integral, okay? And we'll take the expected value of the entire thing. Okay, so we will process all the possible values of theta across 0 and 1, and we'll integrate them, and we'll weight certain values of theta more heavily and other values of theta less. Okay, this is probably the best approach, or I guess most accurate approach. This will give you your expected value, but it can be tedious, and so the final approach, and this will be kind of the motivation for why we do Monte Carlo, is we can kind of estimate this expected value via Monte Carlo. All right, so let's take a look at each of these. Then let me go ahead and give you your second view quiz answer today is the letter C. C as in cat. C is your second view quiz answer, C. Okay, one is we're going to just take a single value and plug that in. So our posterior distribution has shape parameters 86 and 224. So we said, okay, your mean is going to be alpha divided by alpha plus beta. So 86 divided by 310 gives me 0.277. And so we plug in 0.277 into our thing, into where theta is 3 choose 2, 0.277 squared times 1 minus 0.277 whatever, and you get 0.1668. All right? Okay, there's your answer. That's what you get if you plug in the mean. The mode is slightly different. It's not 0.277. Remember, the mode tends to push things out towards 0 and 1. So instead of 0.277, you get something a little bit lower than that, 0.2759, okay, or 0.276 basically. Okay, so just ever so slightly different. You plug that in, you get a just ever so slightly different number. You get 1.65 or 0.165. Okay, so when you plugged in the mean, you got 0.1668. When you plugged in the mode, you got 0.165. Okay, so I mean at this point, it's kind of hard to make a huge argument for this because at the end of the day, is it going to make a huge difference? Probably not a huge difference. Okay, but sometimes you want to get something reasonably, justifiable. And it might be tough to justify that you're just using one number as your estimate, okay? Okay. The other thing we can do is we can try to find the expected value, okay? And so, so here we're gonna say, all right, I wanna calculate the expected value of this function g of x of some random variable x, okay? And we know the probability distribution of x, but we don't know the distribution of g of x. So we could say the expected value of g of x is the integral across all possible values of x of the function g of x times basically the PDF of x, okay? So in our case, the PDF, this f of x is going to be equal to the beta distribution here. And then g of x is going to be the probability of getting 2 hits and 3 at-bats for some unknown parameter theta. So we're going to kind of put that in here. So we're going to take the integral across all possible values of theta. So integrating from 0 to 1 of g of x, the probability of getting 2 hits out of 3 at-bats, times the PDF of theta, which is our beta distribution with shape of parameters 86 and 224. So we have this. Okay, and so this is kind of a big pain, but we'll go through it. And this is, again, this is the analytic approach, right? And you know, luckily in this case, it is solvable. And so when you do the analytic approach, okay, I'm gonna, we'll do 3 choose 2 is evaluates to 3, and then this beta function 86 224 can get extracted because it's just a constant. And then over here, I've got the integral from 0 to 1, and I got theta squared 1 minus theta, theta to the 86 minus 1, 1 minus theta to the 224 minus 1 d theta. We combine all of these things, we get theta to the 88 minus 1, and 1 minus theta to the 225. Okay, now that we're adding these things, okay, 225 minus 1. And so, again, we're using kind of that relationship where, you know, the integral of this thing can be evaluated to our beta function. So we get beta function with parameters 88 and 225. Okay, so we will expand this out, okay? So this becomes gamma 86 times gamma 224, and then on the numerator we have gamma of 86 plus 224. And then over here we have gamma 88, gamma 225 divided by gamma 88 plus 225, okay? So 86 and 224 add up to 310. 88 and 225 add up to 313, okay? And so now we'll just go ahead and use the factorial equivalence of the gamma function. So this is 309 factorial, 87 factorial, 224 factorial, 312 factorial, 85 factorial, and 223 factorial. Okay, so 312 factorial and 309 factorial, that's going to be 1 over 310, 311, 312. 87 factorial divided by 85 factorial will be left with 87 times 86. And 220 factorial, 4 over 223 factorial is just 224 on the numerator there. Okay, and we have a 3 over here. And so all of this comes down to 0.167. Okay, so that gives us a little bit more precision, or I don't know, our expected value. And we can see how does that compare. So we have 0.16715. If I go back, when we plugged in the mode, we got 0.1654. And when we plugged in the mean, we got 0.1668. Okay, so this one is, this one's our expected value. Okay, so that is getting our expected value, and we took an analytic approach. That was fine, okay, but I don't know. This feels like a pain in the butt, right? And I think if I were to give you, like, I'm not going to do this, okay? I don't think. Like, if I were to give you this on an exam, you would be mad at me, right? You'd be like, oh, I can't believe you put that test on, or problem on the exam, because this feels like, oh gosh, who's going to know all of this off the top of their head and to do this, right? Like, okay, so anyway, trying to do take the analytic approach. Yes, it's if you can do it, great. But if you can't, like, that's completely reasonable. I wonder how good ChatGPT is. Like if I said, hey, I don't know, ask it. Just say, can you calculate the expected value of this thing? Maybe it'll figure it out. Okay, and show your work. Okay, so this is where we're going to introduce Monte Carlo methods. Okay, so with Monte Carlo methods, we can say, well, this is what I want to do, right? I want to get kind of a good estimate of the analytic approach, okay? But I don't want to do this integral. I don't want to integrate across all of the possible values. So instead, we say, well, what is the function that you want to figure out, okay? The function we want to figure out is 3 choose 2 theta squared 1 minus theta to the 1, okay? So I'm going to just code that into R, and we're going to just call that G. Okay. So this is going to be the function, okay? And we're going to just do 3 choose 2, which is 3 theta squared times 1 minus theta to the 1, or just 1 minus theta, okay? And then rather than trying to integrate across all of the possible values of theta, where theta is coming from the beta distribution with shape parameters 86 and 224, rather than doing that, the Monte Carlo approach just says generate at random like 1,000,000 values, okay, from this beta distribution. So I'm going to just say R beta, generate 1,000,000 values from the beta distribution with shape parameters 86 and 224. So now I have 1,000,000 values generated from this, and this is going to have the natural kind of property that more common values, okay, values where it's more common, so values near, 0.277-ish or whatever the mean and the mode are, those values are going to appear more frequently. Values that are unusual, like values close to 0.9, values close to 0.05 or whatever, those are going to appear very, very, very infrequently in my random sample of 1,000,000 values, right? So we have 1,000,000 values, and sure, we might get 1 or 2 out of 1,000,000 that have that are really rare, but overall, most of the concentration of values will be in the areas where it's more common. And then so all we do is we just plug in every single one of those 1,000,000 values into the function, and the computer is able to do this very quickly. So it's going to say, okay, when you got 0.27785, this was the value of G. When you got 0.2643, this was the value of G. When you got 0.25587, this was the value of G. And it does it for all 1,000,000 values. And then we just say, okay, you've calculated this quantity for all 1,000,000 values. And again, more common values show up more frequently. What is the mean of all of that? And when you do that, your estimate of the mean is 0.1671577. Okay, how does that compare to the analytic answer? Very, very close. Okay, so the analytic answer when we plugged in everything was 0.16715, and I guess 1515. Okay, 0.1671515 is the analytic answer, and then here's my Monte Carlo estimate. I'm getting 0.1671577. Okay. So very, very, very close estimate between the Monte Carlo estimate, where I didn't do any analytics, right? This is 4 lines of code. I set a seed, which is optional, but generally recommended for Monte Carlo methods. We set a seed, we generated random values, I plugged that into a function that I wrote, and then I took the mean of G applied to that sample of values. And then so when we do that, we get this estimate. So, when we compare kind of the Monte Carlo estimate, we get a pretty good approximation. Okay, again, that's the whole thing. In Monte Carlo methods, you're not going to get an exact answer. You want an exact answer, you got to do the analytic approach. Okay, but here we're saying close enough is good enough, right? And And so that's what we're doing, okay? And usually, it's a lot easier to just think about like, okay, I'm going to just generate random values, and then I'm going to take the average. And that's kind of the whole approach with Monte Carlo methods, is that we just say, I want to just generate random values, and then we can kind of take the average rather than trying to do an actual integral here. So I'll have to remind later. Okay. So again, so the idea here is we'll do a different seed. Okay. So I'm going to just generate a sample, and here we want, from the beta distribution. So I'll say like 1,000,000 values. Shape of parameters, 86, 220, what was it, 224? Okay. And then, if I say, hey, give me a histogram of the sample, is this not how do you set the, why is my thing broken? Oh gosh, I broke something. Remind me later. All right. Okay. All right, so what did we do? We sample R beta 10 to the 6, 86, 224. Okay, how do I set my Y limits on histogram? I always forget. Xlim, Ylim, right? Oh, I want the Xlim, not Ylim. You're right. Okay, so I want histogram of my sample with the X limits equal to 0 and 1. Is that right? I'm like scared. Okay, so this is what it looks like, okay, when we generated 1,000,000 values. And so just naturally, values that are more common appear more frequently, values that are less common, and then say, if I just say, hey, what are the first, say, 20 values of this, okay? So we can see, values like 0.277 or whatever. What do we say the mean is? So the mean is supposed to be, 86 divided by 86 plus 224, so 86 divided by 310, so that's the mean. And I could just say, hey, what is the mean of my sample, okay? And when I generated 1,000,000 values and I calculate the mean, it's really close to what the theoretic mean should be, okay? And so again, I can just kind of plug in all of these things. I have to create a function. This is the function that I want to create. I'm going to do 3 times x squared times 1 minus x, or I guess theta, okay? And so we're going to just plug in g of our sample, and this is going to give me 1,000,000 values, so I want the mean of that. And so I get 0.671517. Oh, that's even closer. 0.16715. What is it? Something like that. 1517. So this sample was even closer to the analytic solution. Okay. And so anyway, that's where we are headed. Okay. So the whole point is, a lot of times, so in Bayesian stats, your posterior distribution is a random variable. You've got a probability distribution. You probably have infinitely many values to think about. And so how do you get your answers? Okay, you can plug in one value at a time, like the mean, or you plug in the mode. Okay, probably the preferred approach is to get the expected value. Doing the analytic approach for the expected value is often painful, and so we'll take the Monte Carlo approach to do this. Okay, all right. We will end here, and let me give you your last VUE quiz answer.